How are you guys doing? You ready for the weekend?
Yes.
It looks gonna rain though. Probably that's good. It's good for sleeping. Okay, so we're going to start right away with the homework. So I'd like that you start working on this problem. Problem number 1. So the homework for next week is going to be problems 1 to 4. And then for the next week, we'll complete the problems 5 to 7, I believe. So I guess you already know about this, about the strike and dip. So I like that you convert all of these azimuths, which are written in the quadrant convention, to the azimuth convention, okay? So you can get started working on this, and then we'll discuss about the solution if you have any questions, okay? I also will suggest that you start for each problem from each of these 4, that you start drawing the stereonet, okay? And I don't know if you remember quite well how to work with stereonets, but here you have an example, okay? But I'm going to suggest that if you need, you can use some visual aid now in the homework and also in the exam. Actually, if you need something to help you in the exam, to me that's fine. You don't have to imagine everything in your head, but lately when you learn how to interpret this, you're not going to need it. But for example, I did this myself. Okay, you can do something similar. Remember that what I want you to draw is that point. At this point, if you want to draw that line, that's still okay. But later on, I want you to be able to interpret just what the point is. But if you want to draw the line, that's fine. And remember that the point is going to be the intersection of this perpendicular line onto the lower hemisphere projection. So that's what's called the pole, and that's where the dot is going to be, but that depends on the orientation of the plane. And there is just one solution for each plane. Okay? If you stop by my office, even if you stop by to say hello, I'll give you 3 cards. One to do this, and another one to do this that we're going to see later on. That you can also use it in the exam, in the homework, whenever you want. Okay? All right, so please start working on problem number 1. And let me know if you need any help. Yes. Yeah. So this stereonet is, remember, it's like a half sphere or a half dome. And what you're trying to do is, if you have a plane over here, when you have a perpendicular line, is the intersection of this line with that half dome. And what you see from the top is this. And that intersection are those points.
So if it's closer to the middle point, it's technically a flatter plane.
Correct. Yes.
The farther you go out,
Yes. So probably it's easier if I do it over here.
yeah.
If you have a vertical plane, it's going to point right here. I'm sorry, horizontal plane. If you have a vertical plane, it's going to point anywhere, in this case here, or if the strike changes, here or anywhere in the outer edge of that projection.
Is your green pen in the middle of the plane?
No, the green pen is the perpendicular line, what is called and the tip is the pole.
Yeah. Okay.
Okay? So I see that many of you, you also have a computer with you. Try to use that web application after you solve it on your own, okay? Just to verify your answer. But that one is very useful to also understand in 3 dimensions what's going on.
I know, would it be like right here?
Mental math exercises, like load.
So that would mean 55 degrees. Okay, I don't have the second part. 45 south. Yeah, that's the next part. So, do I go like the southeast and then 45 here?
So like it's 45.
Yes. Towards the south, it would be this way, or like the ditch is facing this way. So it'd be like, it would be this would be a certain way. It would be 45. So you know how to get this far?
What is the angle?
I mean, it was going to get a wheel. That means we can go down 45 degrees.
This is 55. Stop at 55. And then it tells you go towards the southeast, okay? And that means that the plane is somewhere there. But notice that the strike is still the same. Okay? The zero would be there. Flat. That's 0 deep. And it's 90 degrees deep. So if it's 45, you have to go from 0 to 45. Stop right there.
But I mean,
And then the final solution is to get a point which is perpendicular to this and intersects the lower perpendicular. 45 plane is there. Perpendicular to that plane, you will find the pole, which is
So your dot will be 45 degrees.
Okay, so.
Let me check if I can do it. Sure.
There's the line and the dot, or just the plane? No, I think the dot.
45 is an angle.
You don't need the way, where do you go?
And then it's also
It tells you the position in angles of the line, this line, and the plane.
what are they supposed, like, what values?
Okay, so
this is 45, right? This
okay, guys, let's talk about the solution for problem number 1. Okay, so here it's not too difficult to see what's going on. It's a little bit easier than on just a 2D projection. So here you see I clicked on the pole. That's a point that you have to draw. And at that point, you can see that the plane, it tells you, it says plane S and D, right? The strike is 55, the dip is 46. So for example, if I had the same strike but a dip of 90 degrees, I would go somewhere over here. If I had the same strike but a dip smaller, I would be somewhere over here. So for the same strike, the dip is going to vary from here to there, straight line. And if you look at this, let me do 3 cases with the same strike. So I'm going to do another one here and another one there, and we'll look at this in 3D, and those are those 3 planes. The green one, let me move this a little bit. Okay, the green one is a solution for 45 degrees. Remember, this is the north, so it's dipping towards the southeast. When you look from the top, if you were to drop a droplet of water, it will go towards the southeast. This is the south, this is the east. And this is the one with 45 degrees. This one has a dip of, let's say, 30 degrees more or less. This one has a dip of about 71. Well, actually, this one is 22 and 71. Okay? All those planes, they have the same strike. That's the first number. The second number is the dip. You could also have a case that it could say for the same strike, this one, the plane may be dipping towards the northwest. So in that case, the points will be on the other side. The planes will be dipping towards the northwest, but the points will be on the other side. Okay? And
I have a question.
yes.
So the inside
The green here.
It's 71, right?
This one, the red. This one is 71.
And that's the inside plane here? Like at the top, it would be like the...
At the top,
Yeah.
it looks like that.
So that's the closest ring. On the homework page, we have 90 degrees on the outside. It goes from like 90 in, right? So that's,
You're talking about the second one, or?
well, just like on number 4, how it has like slip is, or dip is 90, right? On the outside. And
Yes.
And then the 70 though on that one is like it's closer to the 70, right?
Yes, 71. So let me add one more then.
Okay.
Let me add one close to 90. It will be a plane somewhere over here.
Oh, okay. Thank you.
And if we now look at that in 3D, is that plane. You see it's almost vertical, and the pole is right there. If you look from the top, that has a dip of about 90 degrees. All right, so you can use this application, but as I told you too, you can use, remember anything, a plane. You could use, in the exam you're not going to use your phone, okay, but you may use your calculator as a plane. And remember that the point is just the line perpendicular to the plane and always pointing down. Don't do something like this. Like they say this is the plane and the line is the one that is going up. Always has to go down in order to intersect the lower hemisphere. So it will be this one. Yes?
On number 3, what would be the answer?
For number 3, let's see.
It says no, 20 degrees west.
Number 3, this one?
Yeah.
So it's the strike would be from the north 20 degrees towards the west. So the azimuth will be 360 degrees minus 20.
Okay, so it's not going to be, because if you strike that, then it would also be 160. So 90 plus.
Okay. Actually, you are making a very good question here. So it depends on the dip too.
Okay.
Let me come here to the front. So we know the strike somewhere over here, right? But now we need the dip. We don't know if it dips like this or like that. So in this case, the dip is 25 degrees towards the southwest. So it is like that, right? So in this case, actually, this strike is going to be 180 minus 20. Okay?
Like 25 degrees southwest should be turned like this and above and down. So the dots on the northwest where it intersects the bottom or the northeast.
Southwest, yeah, like that. So then the angle is going to be this one, 180 minus 20. That's it. If you get very picky with the azimuth convention, okay? But if you gave me the answer either 360 minus 20 or 180 minus 20, I'll consider that. That's okay. But in fact, it will depend on also in which direction the dip is going. We're going to explain that a little bit later on, but you can also put the coordinate system here, like this, and it will depend on which direction this one is going. The direction of the strike is going. Okay, so let's talk. I'm sure that you're going to be able to solve the other ones. It's just a repetition of the others, the first one. So let's talk about problem number 2 and 3 and 4, which are about the same, but it's just that this one starts from a different. It's a reverse problem to 2 and 3. Okay, so these two problems, 2 and 3, are about finding ideal orientations of hydraulic fractures and shear fractures. Remember that we said that always we can find the ideal orientation of a hydraulic fracture by finding the plane which is perpendicular to the minimum principal stress. The hydraulic fracture always going to be a plane perpendicular to the minimum principal stress. But now we're going one step further. We need to find what is the ideal orientation also of shear fractures. And in order to do that, we need to know not only the state of stresses, but there is one more variable, and that variable is the friction angle. So we did already one case with strike slip, and we found an ideal orientation of the shear fractures in strike slip. And remember that here the dip is just 90 degrees. It does not depend on the friction angle, but the strike of these shear fractures, it does depend on the friction angle. In this case, we assume the friction angle to be 30 degrees, and therefore the angle beta is 60 degrees in all cases, and that is what controls here the strike of these faults. Okay, there was one more thing that I was missing from here, and is that, as I just said before, this angle beta is 60 degrees, is 45 degrees plus the friction angle divided by 2. And if you remember, we can also get that and see that in the Morse circle. In the 2D Morse circle, we said that we're going to find the point of maximum ratio of shear stress to normal stress at an angle of 2 beta from the plane of the maximum stress to the plane of minimum stress. So for now, please just concentrate on this big circle. The big circle here has a center somewhere over here, and that point is going to be located from this center of those 2 points at an angle of 2 times beta, which in this case is 2 times 60 degrees, and is at that point where I find the maximum shear to normal stress, and that's what also controls the strike of these faults and also the orientation of those. So before we go to the reverse faulting, let's just do as a rehearsal the easiest one, which is the one for the normal faulting. Okay, so for the normal faulting, I'm going to draw again this block with the longest direction along the maximum principal stress. Remember, if this is normal faulting, the maximum is going to be SV, the minimum is going to be SH min, and the intermediate is going to be SH max. All right, so can you tell me now what is going to be the strike of the shear faults that I should obtain with this configuration, again taking into account this state of stress, and also a friction angle equal to 30 degrees. But actually, you don't need a friction angle to tell me the strike. What will the strike of those faults be? I hear 0. Any other suggestion? Remember to look always at these planes as a combination of the maximum and the minimum. The maximum is SV, the minimum is SH min. So it's going to be a plane that probably would have a hinge on this line, and it's going to go from this plane over here, the plane of the maximum principal stress, to the plane of the minimum principal stress, which is this one. So yes, it's going to be 0, and I'm going to choose now a plane that dips towards the east, But as we said before, we could also have a solution in which this will be dipping towards. I don't know. Okay. This could dip also towards the west, but the strike is going to be exactly the same. It's going to be 0. And now, what is going to be the dip of these faults? This is number 1. This is number 2. So 1 strike, 0. And what about the dip? What is the dip of number 1? How much? 60 degrees what? $60 degrees east, right? It's going 60 degrees towards the east, plane number 1. And plane number 2 is also going to be 0 degrees. You could also sometimes say that this is going north-south, and the dip for this one is going to be also 60 degrees, but in this case west. Where does the 60 degree comes from? From there. 60 degrees is this angle beta, and also this angle beta 2. Any of those is beta. And I was telling you that if you stop by my office, then I'm going to give you 3 cards. And with this, you can remember this pattern of this X. This X is always going to be aligned with the maximum principal stress coming in this direction, the maximum here, and the minimum from this side, and the intermediate with the axis of the X. Okay? So in this case, you can see very clearly for normal faulting, this will be the orientation. For strike slip, now the orientation will be like this. But now this is SH max, which now this is the one which is the maximum is in this direction, and the minimum is in this direction, and vertical aligns with the axis of the X. And for reverse faulting, it's going to be exactly the same. But let's finish the normal faulting, and then we'll go to that one. So let's do the stereonet for this one. I know that by now you are all very proficient in stereonets. So what is number 1? The strikes is 0, so it's the line somewhere over here, right? So the dip is just going to be somewhere over here. So tell me stop for number 1. 60 degrees east, right? This is number 1. And what about number 2? Right there, 60 degrees. If we draw the Morse circle, now we have as a maximum stress sigma V, a minimum stress sigma H min, and this is going to be the circle, and let's say we have an intermediate somewhere over here, sigma H max. The center of this circle is going to be, considering these 2 points, somewhere over here, and if this is a failure, this angle is 2 times beta. And let me just draw the other circles. There will be one over here, there will be another one over there. But let's not worry about those circles right now. The most important thing is to recognize that point, where here I have 1 and also I have 2. Okay, so now I want you to work on number 3 on your own, okay? I'm going to tell you what are the conditions here. For reverse faulting, also I'm going to draw the maximum, wait, let me move this a little bit to the left. The maximum horizontal stress striking in direction north-south, with the axis also going in direction north-south. So this is going to be SH max. This is going to be SV, and this is going to be SH min, where in reverse faulting SH max is larger than SH min, larger than SV. So tell me what is the strike of the two and deep of the two possible faults. And again, the only thing that you have to do is to apply this rule to that one, and that's it. Okay? And I'll place also the X somewhere over here so you remember how to use the X. All right, so work on that, and let me know if you have any questions. Yes.
Could you explain the Morse circle on normal faulting again?
Okay, so the normal circle and normal faulting is this one, and well, this is sigma n and this is tau. So what part?
I don't know. So we're not drawing the two small circles in the middle.
I'm just drawing those for the sake of completeness, but I haven't explained so far what they mean. But I'm going to explain that immediately after we're done with this ideal orientation of faults. That's what comes after what we're doing right now. In the meantime, as you work on that, I'll work on my stereonet. Yeah.
Why was the dip 90 on the, I think that's the normal case?
This one? The dip is 90 because remember that it's a plane which is a combination of this vertical plane and this other vertical plane. So a combination of two vertical planes must be a vertical plane. And the dip of a vertical plane is 90 degrees. So try to think, on this combination of planes. As I told you, the intersection of those two planes, you can think of as that as a hinge, and any plane in between is going to hinge on that hinge. Yeah,
Does that mean for the strikes, the friction angle is always 90?
correct. Yes. Yes.
In the homework you give us mu is 6.5.
So yes, in the homework I give you mu. So if you want to calculate the angle, just you have to do the arctangent of mu, and that's going to give you the angle. Yes, sometimes the geological community likes to work more with friction coefficients, and engineering community likes to work more with friction angles. So we're half done with your exams, okay? There's just one problem I have to grade. If I feel in the mood, probably I'll do it this afternoon, okay? I'll publish the grades also this afternoon if possible. Yes.
If I had like a water side, I would East-west, should it be like this? So is that right? Like this is east-west base. Oh,
Here it's 30. No, it's but a values. Yes. Okay. I think we have just 3 minutes, so I'll talk about the solution now. Okay. So. All right, guys. I hope that you worked out the solution on your own, but just a little bit of language clarification. When I write SHMAX strikes north-south, as in this example, I mean the direction of SHMAX goes from north to south. The arrow is aligned north-south. Remember that in this example, we have this coordinate system where north is going in this direction, south is going in the opposite direction. So this line is aligned with north-south. That's what I mean with strikes north-south. Okay? So for this case in which SHMAX strikes north-south, this is the maximum principal stress. That's why I hatch a little bit this plane. The plane of the minimum principal stress is this one. So these faults are going to be a combination between this plane and that plane. And where exactly? At an angle beta from the plane of maximum principal stress to the plane of minimum principal stress. So it will start somewhere over here and stop at an angle beta. Okay? So let me just draw it a little bit further away so the drawing turns a little bit nicer. One solution is going to be this one, in which this is the angle beta, and another solution is going to be one over here, in which now this angle is beta. Okay, so easy question. What is the strike of these two planes? 90, okay. Or I could also say, let's say east-west. And we're talking about the plane, right? This is the strike of the plane. What is the dip? So raise your hand if you say 60. It's 30 degrees, right? That's where the trick is. In normal faulting, it happens that beta is equal to the dip. But in reverse faulting, you have to do 90 minus beta. So actually the dip, this one is 30 degrees towards the north. This one is 30 degrees towards the south. Okay? Problem number 4 is a little bit more difficult because the stresses are not aligned with east-west. So try to do it, but if you can't, we'll discuss about that on Monday. Okay? See you guys. Have a great weekend.